So continuous random variables. So here in the case of continuous, so we were talking about discrete random variables, right? So the random variable can only take on discrete values, right? So in that experiment where we had a lot of balls, in fact 8 balls in our bag, and we were randomly selecting a ball, right? So there we were dealing with a discrete random variable. Our capital X was a discrete random variable, as it can only take a discrete set of values. But in the case of continuous random variable, uh, that is not the case, right? So in the case of a continuous random variable, when we say probability of capital X is equal to small x, this is always zero, because that is not defined at a particular point of time. So in the case of continuous random variable, we'll always need to take intervals into account, right? So we cannot hint at a particular value and we'll say that, yeah, the probability of capital X is equal to that particular value. So that's zero in the case of continuous random variable, and that concept will become clear in just a while. Okay, and in the case of continuous variables, right, we always take intervals into account, right? So probability of, let's say, capital X taking a value less than greater than a and less than b. So this is uh, defined as the area under the curve of the probability density function, PDF from A to B, right? So this is the small f, not the capital F, remember? So this is the probability density function, PDF, and then there's another CDF, which is the cumulative probability function, right? So do not get confused between these two. So our probability associated with this particular interval, that is a comma b, is represented by this particular notation, that is probability of capital X greater than a less than b, and this is the area under the curve of the probability density function, PDF from a to b, right? So probabilities can be evaluated by integrating this PDF, which is small f of f of x, uh, and the relationship defines, and this is how we denote in the mathematical notation. So this particular probability is equal to the integral of our PDF with respect to dx from the interval a to b, and this gives us the probability associated with this interval a to b, right? So this is how we define a probability density function for a continuous random variable. Okay, so this is how we define it. So when we take some examples, these things will become clear. Okay, so probability density function. So how dense are the values in the vicinity of x? So this tells you how dense the values are in the vicinity of small x. Uh, so the conditions for a function to serve as a PDF. So there are few requirements that a particular PDF should follow. So one is that this fx should be greater than or equal to 0, and x can take values from minus infinity to infinity, and then the integral of the probability density function with respect to ds across all from minus infinity to infinity, this will be 1, right? So these are the conditions for a function to serve as a probability distribution function. So the area under our probability density function, that has to be 1, right? So how do you read this particular equation? So essentially the area under the curve of our small fx from minus infinity to infinity, it's 1. So that is bound to happen, right? Because we're talking about a probability. So all the total set of probabilities, they will all sum up to 1, right? So integral is another way of just doing a summation, but in this case we are doing the summation over the continuous spectrum, right, rather than discrete spectrum. So this is the this is the definition of probability density function, and these, let's check these two conditions if they hold for any particular example, right? So let's take this particular example, f of w, right? So this is 12w square 1 minus w, right? So let's take this particular example. So I'll just write this. Capital W is equal to 12w square 1 minus w, right? So 0, w less than 1, right? So we need to check two properties, in fact. Okay, so f of w, small w, greater than or equal to 0 in the interval minus infinity to infinity, and then we need to also check the integral from minus infinity to infinity. Yeah, I'm just switching to the Jamboard. I'll just yeah, let me just copy this stuff. So f of capital W is equal to 1. Okay. So I'll just yeah. So Sheets is asking a question. I'll just digress a bit. So he's asking, can you explain again why x not equal to x here, please? So here when I said this basic definition, right? So this is 0, right? So if you do any such integral, right? So let's say you want to find the probability, right? So let's say this is a, this is a, right? So you want to evaluate the probability at x is equal to a, right? So this is, of course, you write f of x and then you integrate with respect to ds. So your lower limit and upper limit, they are 0. So by the definition of an integral, so the area will be 0. Okay. So unless, so of course there are some other function like Dirac delta function for which uh, there is some special case, but you need to understand this particular bit, right? So the limits are the same, right? So for that the area will be 0, right? So I'll come to the visualization part, and this particular bit will yeah, be quite clear, right? So let's delete this, and for this particular example, let's check if this is a PDF, right? So what do we need to check, right? So if this is example of a probability density function, right? So firstly we need to check that, yeah, this function is greater than or equal to 0 for all the w's which are between infinity, minus infinity and infinity, right? So if w is any real number, so for which let's will this function be greater than or equal to 0, right? So here of course this function has been defined for 0 to 1, right? So apart from this, so this function has not been defined, right? So we can say that if w take any value between 0 and 1, this will be positive, right? So so this condition is satisfied, right? So sorry, so this condition is satisfied because for w1, right? So f of capital W small w, this is greater than or equal to 0, right? And because 1 is not included, so this equality thing, of course, is there, but this will not come into picture, right? So the first condition is satisfied. Now we need to verify if this integral is equal to actually 1, right? As in, this is a probability density function for the discrete random variable capital W, right? So this is sorry, continuous. So this is CRV, which is continuous random variable W, and we need to check the if the function which we have written, this is a candidate probability density function for this random variable capital W, right? So let's do the integral. So I'll just take an example. So of course we need to do the integral from minus infinity to infinity. In fact, yeah, I'll just clear a few things from here. Okay. Okay. So this can be written as minus infinity to 0, right? So dw, of course. So I'll not write it, right? So this is dw plus 0 to 1, that is what, right? So w, and plus 1 to infinity f of w, right? So this is 0 and this is 0 because our function is not defined, right? Apart from this particular interval 0 to 1, right? So that's why that function is taking a value 0 elsewhere. Okay, so these two values are 0. Now we just need to evaluate the middle integral and see if this comes out to be 1. Okay, so I'll just use the another frame, right? So 0 to 1, 12 w square 1 minus w dw. So let's try to solve this integral. This is pretty straightforward. 12 w square minus 12. In fact, what I can do, I'll put 12 outside. Sorry. Right, so 12 is outside. Right. 12 outside, and then we have from 0 to 1 w squared dw, and then from 0 to 1 we have w cube dw, right? So this is what we have. So so in this case what we'll have, so w squared dw, I think you guys know w cube by 3, and we need to evaluate this in this particular interval, and that w3 dw will be w4 by 4, and this will be between 0 to 1. Okay, so let's see what we get. So this is 1 by 3, and for 0 it will be 0, and then 1 by 4. Okay, so 12 into 1 by 3 minus 1 by 4 is nothing but 4 minus 3. So 12, 12, and this is 1, right? So this is this particular function is a candidate PDF for our random variable capital W. Okay, so let's move ahead. So now talking about cumulative distribution function. So again, here also in the case of continuous random variable, we can define the cumulative distribution function in this particular manner, right? So capital F of x is defined as minus infinity to x, right? So in this way we define it, right? So this is the cumulative distribution function, right? So for we have seen example for a discrete random variable, the probability distribution function, the cumulative distribution function. The same thing also we can we have seen for a continuous random variable. What will be the probability distribution function and their properties, and what will be the cumulative distribution function, right? So this is the cumulative distribution function, and as you can see, so here in terms of probability so this was the probability distribution function, and the probability between this particular interval is defined in this particular fashion. But if we talk about cumulative probability function, so this a will get replaced with minus infinity, and here we'll have x. Okay, and because our limit is we are using this particular variable as the limit, so we will use another variable, that is t, or you can of course use any other variable, that is z or anything, w, maybe anything. So this is how we define the continuous random cumulative distribution function. So as you can see, because this function is integrated with respect to dt in this case, so and the limit is here from minus infinity to x, so this the whole thing will be a function of small x, right? Function of small x. So this is a cumulative distribution function, or CDF, right, which is defined as this case, right? Probability of x less than equal to x, right? So here we are not specifying the lower bound, so that's why we have minus infinity, right? So this function is a continuous non-decreasing function defined for all real values of x. Okay, so let's take a look at the visualization. So here I have the same function, right? So if I'll just, yeah, so this is the function that we have, right? And we have defined the range for this function as 0 to 1, right? So if we can check the area between this area here, in fact I'll just use the annotator, right? So here this entire area, in fact, right? So this is 1, right? So this area is 1, we have verified it, and okay, and so now our cumulative distribution function will be this. Of course, minus infinity to 0 is nothing but it's giving us 0 only, right? So that's why I have written 0 to x, right? So this is the this fx is this particular bit, right? As you can see, so this is the so we need to just focus on the blue shaded region, right? So here, so this is the cumulative distribution function for this particular random variable x, right? So right, and then let's say if we define 0.5 to 0.6 as the interval, so what is the probability, right? So we can write here, so this will be 1627 divided by something like this, right? So this is essentially what is f of 0.6. I'll okay, so one second. So firstly let me just use the Jamboard. So f of 0.6, f of 0.6 is essentially you're integrating your capital W, so 0 to 0.6, because of course this is minus infinity, but minus infinity to 0 is 0 because the function has not been defined in that interval, right? So we'll write instead of infinity, we'll just write 0, right? And then f of 0.5 is 0 to 0.5 f of capital W dw, right? And if you take the difference between that, so that will give you the area in this particular green zone, right? So this area, so this particular area will be denoted by is essentially 16% or 0.1627. Okay, so this area is that. Okay, so in this way we can visualize what is our CDF and the PDF. Okay, so I'll just clear the drawing, and then you can again confirm, right? So this is our PDF, right? And we check that PDF is an actual valid PDF because the area under this curve is 1, and of course this is defined in this interval only. So we saw that in this interval the area is 1, and this is the cumulative distribution function for this, and as you can see is t dt, and to the interval 0 to 6, and if we define x to be between these two, so this is what our so this particular value will be 0.16. So what is the probability that a value will be between 0.5 and 0.6? Okay, so this is the example of PDF and CDF for a continuous random variable. Okay, so here of course you can calculate the CDF, and that's so CDF is nothing but this particular right. So this is our CDF, and as you can confirm, this CDF will come out to be this particular function, which is W cube multiplied by 4 minus 3W. Okay, so and you can verify the properties for the CDF as well, right? So so this is our CDF.